Okay, guys, so we are in unbalanced forces now. A lot of the things we're going to be talking about are things that you've experienced in the past 2 units, interactions and balanced forces, but now we're going to formalize a few things. All right, the big thing with this unit is we're finally going to go over Newton's second law. So we talked about Newton's first, an object in motion will remain in motion, also called the law of inertia. We talked about Newton's third, every action is an equal and opposite reaction. Newton's second law, there's a very wordy version of it, but I'm just going to summarize it as F net is equal to ma. Your net force is equal to mass times acceleration. Roughly, this translates to acceleration of an object is directly proportional to the amount of forces you put into an object. It is indirectly proportional to how big it is. So if it's a very big object, it's harder to move. All right, so we're going to look at problems, and now that we're in unbalanced, not everything is unbalanced, but most of it is. Some of it might be balanced. So we have to read these problems and ask ourselves, balanced or unbalanced, basically. All right, a person applies a 10 Newton horizontal force to a 10 kilogram mass, initially at rest on frictionless horizontal floor. The person pushes for 20 meters. All right. So we asked, is this balanced or unbalanced? Well, before I answer that, maybe I should just draw a force diagram to describe this. So we can imagine a person is pushing a box to the right, and it's going that way. So the box has a weight, we call that Fg. The floor is going to push up onto the box. It's going to push upwards, so that's Fn. He's applying a force, so there's Fa. They say it's frictionless, so there's no friction. All right, well, I don't have any other opposing forces acting on this block. So this, to me, I think this looks unbalanced. And according to Newton's second law, F net is equal to ma. So I'll say this. If you have no acceleration, you have no net force. If you do have acceleration, then you have to have a net force. So we'll call this, it'll also be constant acceleration. So what we'll learn is that, okay, objects that are balanced experience constant velocity. Objects that are unbalanced experience acceleration. So those are kind of our two realms. So if whatever we did back in the day for constant velocity, that applies to balanced forces. Whatever we did with constant acceleration will apply for unbalanced forces for our problems. All right, they asked for 4 diagrams. I already drew one. I'll redraw my force ones, Fg, Fn, Fa. I'll do my VAD as well. Fg, Fa, Fn. All right, so that's my force diagram, my VAD, my vector addition diagram. We want some others. We have a bunch here. I'm gonna, for time's sake, just so this video is not super long, I'm just gonna draw my 3 motion maps, or not motion maps, my kinematics graphs. So I have an object, it should be accelerating. If it's accelerating, that means its velocity is increasing and it is curving up like that. I know I'm starting at rest, and they give me some other information. We push for 20 meters. All right, I don't know how long I'm pushing for. All right, so now they ask us, let's figure out any of these information that we have here. Whenever you're solving unbalanced problems, you're solving for all the forces involved, so anything on your force diagrams, Fg, Fn, Fa, a net force if there is a net force, acceleration, and sometimes I'll ask y'all to solve for delta x, delta v, or t. So I always kind of treat the first 4, we call these dynamic information, and these are kinematic. These are the bottom part's more quarter 1, the top part's more quarter 2, but you'll see we're combining everything now. All right, so let's talk about the forces. So Fg equal to mg. That's just a basic formula. Our mass is 10 kilograms. Our G is also 10, so we get 100 newtons. All right. According to my graph, I think we can make the assumption that, oh, FG looks like it's equal to FN. It's balanced vertically. Now I'm going to show... All right, sorry about that announcement that came on during it. But so continuing on. So I'm going to show y'all how to solve these forces. I'm going to kind of do it the long way, but you'll see in later problems it's useful to do it this way. So I'm going to sum the forces in the vertical direction. Now, remember back in projectile motion, I can split up vectors into x's and y's. I'm kind of doing that again. I'm kind of splitting up these vectors again, but I'm using forces this time. And I ask myself, am I balanced vertically? So I look at this. It basically, is my box accelerating upwards or downwards? It doesn't look like it. So that means my net force is 0. Now all my up arrows are positive, all my down arrows are negative. Fn, positive. Fg, negative. All right. So I've determined Fn is equal to Fg, and that means that it's equal to 100 newtons. I know this seems very like a roundabout way of solving this, but trust me, later on it'll make it a lot easier for more complicated problems. All right, this next part, Fa, they actually tell me Fa is 10 newtons. All right. Now for Fnet, I'm once again going to sum the forces in the x direction. Am I balanced? And what I find is, no, it looks like I'm not balanced. And it looks like my net force is going to be going this way. That's the direction my box should be accelerating in. So F net x is a value here, which is basically equal to our F net. The only force I have horizontally is Fa. So, all right, well, Fa is equal to F net x. That means it's equal to 10 newtons. All right. Kinematically, let's try to solve these. Do I have any of this info? They give me 20 meters, so I know that delta x is 20 meters. All right. So I know that. Let's see if I can solve for A. The thing that links these guys together, forces and kinematics, is F net's equal to ma. So A is equal to F net over m, which is going to be 10 over 10. So 1 meters per second squared. 1 meters per second squared. Then we'll solve for delta V. Now, that means, so I'm going to go back to my graphs here. This is 1 meters per second squared. We have kind of a lot of information here. I can either start using the areas of these graphs, the slopes, and remember what we did in the past. We can start using our old kinematic equations. I think in this scenario, it's probably best that we end up using some kinematic equation. So I can use either this one. We can use this one. Or we can use this one. And since I don't have really any velocity values other than V naught is 0, I'm probably going to start off with this first one. So I'm going to use this guy. So 20 meters is equal to, so this will be 0, this will be 0, 1/2 a t squared. So 20 divided by 1, let me do this math. All right, so t basically becomes square root of 40, which is 6.3 seconds. And now that I have that information, I'll probably use this formula here. So I know v is equal to 0 plus 1 times 6.3. So my velocity is going to be 6.3 meters per second. All right. I'll say this. As far as this unit goes, I'm not too worried about the kinematic stuff. I'm bringing up the kinematic stuff because, your midterms and real life, it's all these subjects combined. It's not like, oh, here's an unbalanced problem. It's, hey, this stuff is happening. How can you break it down and make it easier to understand? So this is where I start introducing those past units back into all of this. All right. So hopefully y'all are feeling fine. For these next two problems, what I want y'all to do is solve for me FG, FN, F, now there is friction, FA, FNet, and acceleration. Don't worry about the kinematic stuff. Solve for me this stuff. And for problem 3, same thing. There's no more force applied. Draw me force diagrams, draw me VADs of these, and I'll see you next video after y'all work on Tune 3. And please work on these problems, because that's the only way you really get better at these. So you do them first, and then check to see if you get them. Thank you.